All right. Hello, everybody.
Hello.
Just got the notification that we're live.
Hi, Kyle. Good to see you.
Well, thanks for joining in, Kyle. We'll be talking about a couple of the astronomers associated with Yerkes over the years. So, Kyle, if you have any other fun facts that we don't cover, please feel free to throw them in the chat. Hello, Max. Thanks for joining us again. Right. Well, I think we will go ahead and get started with kind of our little introduction. And we will bring our guest, Dr. Nic Bonne, on soon enough. And we will then get into that fun conversation about the tactile universe and get to talk a little bit more in depth about certain galaxies. So, welcome everybody to another episode of the Glassroom Planetarium series. Of course, I am Adam, and with me, as always, is my co host, Katya. And as our professional astronomer here, we will be referring to her for a lot of the stuff we're going to be looking at in Stellarium before we welcome our guest on for a conversation. So, to get started, the first thing I wanted to talk about is kind of this nice, almost plain night sky we have right now. Going outside early in the evening, as you can see, this is just set for tonight. You can still see Jupiter and Saturn coming up in the southeast. Still fairly low, but quite bright and easy to find, and definitely worth any effort it takes to get your hands on a telescope to go take a look at those. But we are not going to be focusing on anything in our solar system today. In fact, we're going to be focusing on where our solar system is and things very, very far away from that. So to start, one of the things that, if you look where you see one of the bright stars named Vega, right around in that area, kind of passing through our sky, you can actually see the structure of our Milky Way galaxy. Now, if you're wondering what I'm talking about and you think I'm a little crazy because there's nothing there, that's in part because light pollution actually prevents us from seeing our galaxy clearly. But if we take the light pollution and slowly take it away down to about what the night sky would look like for people hundreds of years ago to thousands of years ago, you can see the thick clouds of gas and dust that make up our galaxy, or the plane of our galaxy that we are looking into, go all the way across our sky and pass through the trio of Vega, Deneb, and Altair, which make up the Summer Triangle asterism. But we're not just going to be talking about our Milky Way today. We also want to talk about some of the other galaxies that you can find. And galaxies are still relatively new when you think about a lot of the other objects that we look at, considering we weren't fully aware of what galaxies were and what it meant when we were looking at them until only the last 100 years. One of the first galaxies that people were able to notice, and one that in dark skies today is still visible to the naked eye, is a faint little patch of, which kind of looks just like a faint little patch of haze in the sky. Unfortunately, if you go out tonight, you're going to have to wait a little late to actually see this. So we're going to jump forward into August or September, and then we can start to look for an object called M31. And one thing you'll notice, if you can look in the top part of the screen, you'll see that it is up there in parentheses, the Andromeda Nebula. So for the longest time, this was known as the Andromeda Nebula. And even now, you can still kind of see a faint little hazy circle there in that target. Katya, do you want to tell us a little bit about this faint little fuzz and how its significance relates to even some of the astronomers at Yerkes?
Yes. So back in the day, when people looked through telescopes, they saw these fuzzy clouds, like Adam was saying, and it looks like a haze in the sky. And they called these nebulae. Some of these nebulae happened to possess a spiral structure that they saw, and so they were called spiral nebulae. But in 1924, Edwin Hubble, who had actually been previously a grad student at Yerkes, and he wrote his famous thesis there, he was looking at the spiral nebulae through the 100-inch telescope at Mount Wilson. Specifically, he was actually looking at Andromeda back then, which was called the Andromeda Nebula. And he was investigating Cepheid variables. So these are stars that, just like their names might imply, vary in brightness over time. And in the early 1900s, the now famous astronomer Henrietta Swan Leavitt actually found a relationship between the period of a Cepheid, so the time over which it undergoes its cycle from going brighter to getting dimmer and getting brighter again, and its luminosity, or basically the intrinsic power radiated by a star. Using this, one can calculate the distance to a star. And so Hubble used this technique in order to measure the distance to various Cepheids in the Andromeda Nebula, and found that they were actually much further away than any known stars in the Milky Way, like 100 times further. And so this actually proved that the Andromeda Nebula was actually the Andromeda Galaxy. And many of these so-called nebulae out there are actually other island universes. So with this discovery, our universe suddenly got a lot bigger. And later on, Hubble actually went to make a classification system for the different morphologies or shapes of galaxies that were found. And there was a couple different types. And so throughout the show, we're going to show you a couple of different examples of different types of galaxy shapes that we've found. Andromeda specifically is what we call a barred spiral galaxy. I also have it behind me as my background today, uh, taken from the astronomy picture of the day. And so it is a huge galaxy that actually formed by the merger of other proto-galaxies. So it wasn't just created like this. It's actually the closest major galaxy to the Milky Way, and it'll actually also merge with the Milky Way in around 4.5 billion years. So we still got some time, and by that point, the sun should also be expanding into a red giant and swallowing Earth. So if you're around at that point, try not to be in the solar system.
Yes. So, uh, something I don't think any of us have to worry about anytime soon. But it would be really cool if we got a chance to see something like that happen. Now, with Andromeda, that being kind of the closest and brightest galaxies, it was kind of one of the first, as Natia mentioned, to be heavily studied. But there are some other very notable galaxies that are visible in our sky. Now we're going to go back to modern day, because one thing we want to talk about are galaxies that you can actually find in our night sky. One of those galaxies is one that uh, was one of the galaxies that helped inspire a Yerkes astronomer to investigate deeper into our own galaxy. Kati, do you want to tell us a little bit about M101, or the Pinwheel Galaxy?
Yeah, so M101 is a great object to observe, and as Adam said, uh, this, along with another spiral galaxy that we're going to see, actually inspired William Morgan, who was an astronomer at Yerkes, to find and detect the shape of the Milky Way, because Morgan was actually the first one to find that the Milky Way actually has a spiral structure to it. Um, and so this is also a very large galaxy, and you might notice that it's not perfectly symmetric. The bulge in the middle is kind of at the top rather than at the center. And this is actually due because this galaxy has recently interacted with other galaxies. Um, so galaxies can, pass through other galaxies. They can also merge. And so this causes this kind of irregularity in the shape. And this also actually causes a lot of star formation to happen.
Right, so as Katia mentioned, this one was along with another galaxy, the inspiration from Morgan. The other galaxy that we were referring to is actually also somewhat near M101. Now, one thing, if you've watched any of our shows previously, you probably recognize a couple of the names of these stars down here were below where you find M101, as finding this galaxy is as simple as looking just above the tail of Ursa Major or above the handle of the Big Dipper. So you can see the 7 stars here that make up the Big Dipper. And not so far away is a galaxy named M51. And this one is not only a very cool spiral galaxy, but has something unique about it. So you want to tell us a little bit about this one, Katya?
Yeah, so this is commonly called the Whirlpool Galaxy, or as Stellarium suggests, the question mark, well, galaxy, Rose's galaxy, lots of different names. Um, but it's actually not just one galaxy. So this is actually 2 galaxies. The other being the dwarf galaxy that you see on the right of the larger spiral structure. And these are 2 interacting slash merging galaxies. They're around 23 million light years from Earth. Um, and so this is actually the first galaxy that people ever called a spiral galaxy. And so you can kind of see, so when galaxies merge, they don't just crash into each other like collision. They actually do this sort of dance around each other. So you have 2 galaxies basically coming in from left to right, one on the left, one on the right, and they'll kind of like orbit around each other and kind of quickly do a little dance. And eventually they'll settle down and merge, and so their black holes will actually also merge in the center. And so this galaxy is kind of in the process. You can have one of the galaxies kind of going through it and disturbing the structure, kind of like what we'd probably see in M101 if we saw it during the time when it was undergoing interaction. And yeah, as Kate points out in the chat, it's a very slow dance. You're probably never going to see galaxies actually merging like in your lifetime. It takes millions of years to actually undergo that process. So it's something that we have to kind of extrapolate from things like simulations and other observational features of the galaxies that we see.
Right, and speaking of galaxies fusing, a really fun example in our night sky, a bit fainter and harder to see as they are quite a little ways off, are the mice galaxies. You want to tell us a little bit about these ones, Katya?
Yeah. Can you zoom in like a tiny bit more? Oh, there we go.
Absolutely.
Yeah.
There we go.
My video is also laggy. There we go. Perfect. Yeah, so these are two of my favorite, I think, interacting galaxies. They're called the mice, probably because they look like either two mice or like a cat and a mouse. And these are like M51, Whirlpool. These are interacting, and they will actually eventually merge. But for now, we can't see that, so all we see is that they're very distorted and they have like a tidal tail connecting both of them in the center. You can faintly see. And so you can also see that there's parts of the spiral that are blue in color. And that is actually regions where we have young stars that are being formed due to the gravitational interaction between the two galaxies. A lot of times when galaxies undergo merger, this is also an impetus for star formation to start occurring because you have a lot more gas and stuff coming into the system.
Yes, all right, and we have two more galaxies we want to fit in here really quick before we bring our guest on for our conversation. One of which is also in the sky and nearby and has quite a few things around it, but this one looks a little bit different. Why is that, Katya?
Yeah, so while the other galaxies we've looked at are spirals, this is not a spiral galaxy. This is actually either an elliptical or a lenticular galaxy. We're not actually sure. Astronomers are still debating about what its shape is. A lenticular galaxy is kind of in between a spiral and elliptical. So it has a disk, but not large standout spiral arms. Um, while elliptical galaxies are very smooth. And both elliptical and lenticular galaxies have a lot of mostly older, lower mass stars. And so this galaxy is actually approaching the Milky Way really quickly. It has a really high blue shift, which means that the light we see, the light waves that we see coming from it, are actually being shrunk in wavelength. So imagine the waves getting like closer, closer together because it's coming towards us.
And so these kind of galaxies, well, not quite as fun to look at feature-wise. Some of them actually do have some very interesting features. One specifically is one that happens to be very close to M86, which makes sense that it's named M87. And you can kind of see down below something kind of popping out.
Yes. So this is a really cool galaxy for multiple reasons. This is a giant monster elliptical galaxies. It's one of the largest galaxies we found in like our local part of the universe. It has a lot of globular clusters in it actually. And so again, unlike the other spirals we see, this one is very smooth. This is an actual elliptical, so it's just like a smooth kind of ellipsoidal shape. You don't see very many features in it. And it also has a really powerful relativistic jet, so an active galactic nucleus, that actually emits mostly in wavelengths outside of visible light. And actually, before like 1991, Otto Struve, who was a director of Yerkes for a very long time. He was one of the most probably successful directors at Yerkes. He was the only person to have seen it visually, the jet, using the 100-inch Hooker telescope at Mount Wilson. Uh, Another thing is you might have actually heard about this object pretty recently in the news. It has a supermassive black hole in the center that was actually imaged by the Event Horizon telescope last year. And so this is actually the first image of a black hole event horizon that we've gotten. And you can tune into our show next week, where we're actually going to talk with someone that actually helped get the first ever image of a black hole. So stay tuned for that.
Just a nice little tease there for next week. All right, but with that, we are going to welcome on our guest for today. And so, welcome. Nick, would you like to tell us a little bit about yourself and how you got into astronomy?
Sure. So good afternoon, everybody. So it's actually the evening here, but we have pretty long days because it's summertime in the UK at the moment. So I'm joining you from the south coast of England on a little island called Portsea in the city of Portsmouth. And yeah, so I'm an astronomer. I'm also a science communicator. But on top of all of those things, I'm also a blind person. So I can see just a tiny, tiny bit. As long as my head's way up, really, really close to things, as long as I can spend enough time looking at things, and as long as the contrast is high enough. So there are lots of ifs there. But despite that, astronomy is something that's always really fascinated me. So from about the age of 5, when I think the first memory I really have of sort of something astronomy and something that I was really interested in was when the Voyager probes that went out into our outer solar system took pictures of Jupiter and Saturn and Uranus and Neptune and all of their moons and sent those pictures back to Earth. A lot of that stuff was in the news. There were a lot of documentaries. They were showing these pictures, these beautiful full color pictures of the outer planets. And I remember sitting with my head right up against the TV screen and just hitting pause and looking at those pictures and trying to get as much detail in those as I possibly could. And I guess that got my brain going. Started thinking about just how far away those planets were, but then how much further away everything else just in our galaxy would be, and then in the universe. And it got my head going. And from that point on, I was pretty much hooked. I wanted to learn as much about space and astronomy as I possibly. But having said that, being somebody with a vision impairment, it wasn't always easy to do that. So I was lucky in that nobody ever sort of said to me, "You're blind. Why are you interested in this stuff? It's also visual." People were they were pretty supportive, which was nice. So my parents took me to a lot of museums. They made sure I could read the books that I wanted to read to learn. Lots of books with big pictures that I could see properly. But really, in terms of accessible resources, there wasn't a lot available when I was growing up. But yeah, I chased that dream. I went to university. I studied physics and mathematics and got my degree major in astronomy. I went to a different city in Australia. You might have picked up that I have an Australian accent. Went to a different city in Australia, started a PhD. That PhD was studying the way that galaxies rotate because of the amount of dark matter that they have in them. We can maybe talk about that a little bit more later on. But that was using radio data. And I actually got 2 years into that PhD, and then I had a little bit of a breakdown because it turned out moving so far away from family, I'd gotten a little bit cocky. I didn't build up support networks for myself. I didn't get to know enough people. I didn't ask for help when I needed it. And so I actually, I bombed out of that degree. And it took me quite a number of years to decide that I wanted to come back and have another go at trying to become a professional astronomer. And after all that time, after all that thinking, one of my old lecturers from my original university actually offered me a spot running lab classes and tutorials for their first year astronomy students. So I came back and I started doing that. I got talking to some of the researchers in the department. one of them offered me a chance to come back and have another go at a PhD, and I decided to give it a shot. And so I made it all the way through that one. It took me 4 years. And yeah, so that was sort of the dream that I've been chasing for years. So I got through. In my first shot at a PhD, there was a lot of observing involved. So lots of trips to radio telescopes, lots of trips to optical telescopes in sort of the Australian outback to try and collect data to use for my thesis. I kind of moved away from that for the second PhD. I used data that people had already observed. And a lot of my work was basically bringing data together to understand a whole lot of nearby galaxies. So the idea was that I wanted to take all the data that I could find for as many galaxies nearby to us in the universe, all of the galaxies that had recorded shapes or morphologies. So if we knew that they were spirals or elliptical, if they were galaxies that were merging, or if they were irregular galaxies because they had really messed up shapes. If that data existed, then I wanted those galaxies in my galaxy catalog. And so we collected together all this kind of useful information, and we did some really nice sort of studies of that galaxy population. We looked at really unusual things like red spiral galaxies. But I think the problem for me was always when I had to actually double check that the data that I had, that those numbers that made up my catalog, actually matched up with what those galaxies look like, what they'd been observed as. And so I'd bring up my galaxy image and I'd have a look and I'd squint. And sometimes it was really, really hard. So I'd often have to turn to my office mates and say, hey, is this actually red, or am I imagining things? Or can you see a spiral arm if you squint, or is this actually just a really plain elliptical galaxy? So that side of things was always a little bit difficult. Yeah, and I guess that's a nice segue into the tactile universe.
Yeah, that segues wonderfully. And I know
Can
you
I
brought
share
us.
my screen?
Yes, I was just about
Yeah.
to say, Kat, if you'd like to swap to sharing your screen.
Yes.
Might look kind of funky for a second.
Ooh, there we go.
All right, and I think we are set. So, yes, so the Tactile Universe project is something that really fascinated me, and obviously we thought it was cool, and so we put it in the title. So, and we now kind of know why this project kicked off. How did you end up getting involved, and what has kind of come out of it so far?
Yep. So when I finished my PhD, I moved to the UK with my girlfriend, who is now my wife. So she got a job at the University of Portsmouth. I didn't have a job to start off with, so I was just finishing off my thesis, doing some research, just kind of killing time while I looked for work. I started to find that I was running into the same problems again. I was coming up against these double checks that I had to do to actually look at the galaxy images to make sure that what I was seeing was matching my data, and it got me thinking that even though, so when I was a kid, there wasn't a lot of stuff that I could use to learn about astronomy, that was still kind of the case. So there were a few projects around that had done things and had done a really good job of them, but there wasn't enough in the way of resources out there to help people like me who had low vision or no vision, especially to learn about things like galaxies. And so I actually had a chance conversation with Kate Meredith, believe it or not, who runs Glass Education. And she asked me lots of really, really deliberately sort of pointed questions and got me thinking about what I could do, what would have helped me in my PhD, and what would help other vision impaired people learn about galaxies, learn about astronomy. And so when it comes to astronomy, a lot of the time we are stuck with these images because that's the way that astronomy works. It's the way that it's always worked. It's not necessarily the way that it should work, but when we teach astronomy, when we learn about astronomy, when we publicize astronomy, everything is very, very visual. And so we wanted to take that visual side of things and make it more accessible. So I believe I described to Kate that what I wanted to do was take the light from a galaxy image and make it tactile, and basically make it more tactile if that light was brighter, make it less tactile if that light was dimmer. So I sort of had this almost height map, I guess you could think about it, like a height map. I had an idea in my head of what I wanted, but I wasn't really sure how I was going to make it. It so happens, though, that one of the slightly more technologically savvy people at my university had an office across the corridor from where I had this conversation with Kate via Skype. They overheard my description and they knew enough about 3D modeling that they actually went away, and a day later they knocked on my office door and they said, "Nic, is this what you were talking about yesterday in that meeting you were having?" And my colleague Coleman had basically made the first tactile galaxy model that sort of is the basis for the Tactile Universe. And I think we have some 3D versions of these that we can maybe look at.
Yeah, I have some M51 models.
Yep. So M51 was our first galaxy. It's a really cool looking galaxy. It's one of my favorite galaxies as well. So we decided we would use that as our prototype. Hey.
Once it decides to work.
If this actually works.
There we go.
Okay, so this is an image. So this is the first lot of galaxy models that we made. This is using the digitized sky survey, which is the first real attempt that was made to actually create a digital database of galaxy images. So it's data that came from a lot of different telescopes. You can see on the far left along the bottom, we have the back sides of the images. Along the top, we have the front sides of the images. From left to right, we're basically starting off with the bluest filter that they attach to that telescope. In the middle, we have the red filter, and then on the far right, we have the near infrared. So not quite infrared, still in the visible, but very much towards the edge of visible. And those images change. So this is the way that astronomers observe things in space. They don't look at something and get this beautiful full color image. All of those beautiful full color images of galaxies that we see in the media and in textbooks and other things like that are actually, usually it's a red, a green, and a blue light image of that object that are stacked together, and that basically creates the full color thing. So we want to do the same thing with these models, because obviously if you're feeling a color image, there's no way that you can tell which bits are blue and which bits are red. It'd just be too difficult. So we decided to do things the same way that an astronomer would with a telescope. We use the individual colored images. So we use the image that picks up the blue light, the image that picks up the red light, and the image that picks up the near infrared light. And I don't know, do we have any vision impaired people in the audience?
I don't think.
Not sure.
No.
Okay, so I'm going to assume that all of you can see what I'm talking about. So you can see just how much the structure in these three images changes. So on the far left, we've got lots of detail in the spiral arms. There's all that beautiful feathering. So all these really bright regions where there's a lot of star formation going on in this galaxy's spiral arms. If you print this image big enough, you can actually feel a little dip running through the very middle of those spiral arms where the dust lane is. So there's this big region of sort of darkness that runs through the very center of all of those. When we go redder and redder, you'll notice that those arms start to drop off. So those regions where we're getting all of that star formation. And all we're left with is the regions of the galaxy that are really, really red. So there's the bulge in the middle, and there's the companion galaxy as well. And so this is just an example of one of the galaxies that we've turned into a series of tactile models. But using the fact that we can talk about color and the fact that we can talk about the shapes of these objects using these tactile images, we can get a lot of information across to people about, I guess, the past, the present, and the future of these galaxies, these particular objects. One thing I should point out as well, so along the bottom here, like I said, is the backside of the image. This image that's stuck on, this is the original telescope image. We've actually mirrored it so that when you look at that side with the image, you can touch the tactile features and they'll be exactly what you're seeing. So we wanted to make sure that these images would work in a visual way as well as a tactile way, or as a combination of the two if people have a little vision. Because as I'm sure a lot of you realize, everybody with a vision impairment is different. Everybody's unique. Everybody will use a little bit. If they have a little bit of sight, they might use that. They might choose to just use tactile, or they might choose to just use audio. It really is up to the individual. So we wanted to make sure that these models would work for people no matter what mode they wanted to use to interpret them.
Gotcha. Now, one thing I was wondering, are there certain galaxies that are a little harder to represent 3D that way, or are elliptical galaxies a little more tricky?
Ellipticals are a little trickier. So if we could maybe bring up a picture of an elliptical just so we talking about. So one of the advantages of spirals, especially ones that have got a lot of star formation going on, is of course there are lots of really abrupt changes in brightness. So we have a steeper gradient in the tactile features that you can actually feel. The problem with an elliptical, though, of course, is that it really is just this gradual gradient from a bright center all the way to the edge of these things.
I think
Thinking about it.
It is thinking about it.
yeah, the view is kind of small, but you can kind of make out how the core is very bright, and then it does kind of fade.
There you
It
go.
fades,
I'll just
fades
zoom in.
towards the edge. So yeah, these are a little trickier. So you will actually feel a gradual slope up to the top and a gradual sort of slope down again. I actually really like the tactile image of, so we don't have an example of the tactile image of this one. All of my models are actually stuck at work, and the building that I work in is closed because of the coronavirus. So I can't really get anything out of there at the moment. But we can talk about it just based on this image. So if you run your finger from sort of one corner to the other, you will feel that gradual increase, and you'll feel that sort of peak in the middle, and then you'll feel that gradual decrease again on the other side. Now, when we look at this galaxy, I think most of you would agree that we see a definite edge to this thing, right? So we want to see it as a sort of football shape, rugby ball or a football. We want to see this definite edge to this object. The way these galaxies actually work, though, is these are mostly made of red stars. What we're seeing in terms of the change in brightness is just a change in the density of that stellar population. So in the very center, there are a lot of red stars all really grouped sort of closely together. As we move further and further away from the core, we're seeing less and less density, so that brightness is dropping off. What actually happens with these objects is they don't really have an edge per se. What will happen is eventually the density gets low enough that it's the same as the space surrounding that galaxy. And when you feel the tactile model, there is no definite edge. You literally just slope down into the space, sort of the background darkness. So there's no defined edge. Whereas when you look at these images with your eyes, you're kind of tricked into thinking that they have this definite shape, this definite edge. So in this sense, the tactile image actually gives you some advantages because you're feeling something a little bit more like what this object actually is. Where we do run into a little bit of trouble, though, is in objects like red spirals. And if we can bring up an example of a red spiral.
Do you have a name?
Yeah,
one?
bottom.
Oh,
so
yeah.
the bottom.
This one.
Bottom
Bottom?
left-hand corner. Yep.
4305.
Yeah, this one.
4305.
Yeah, that's what I thought.
Yeah.
Yep. So these objects are a little bit tricky. So I looked at these quite a lot during my PhD work. So these things are as massive as galaxies like our Milky Way. So they're as massive as our big sort of blue star-forming spiral galaxy. But as you can see from the image there, these things don't have a whole lot of blue in them. So they're mostly red. So what we know about these objects is they do have really, really low levels of star formation. What makes them odd, though, is most of the other red things that we see in the universe are really smooth. So like our elliptical galaxies, they have these really smooth profiles. You can see a little bit of that in this object, but you can also see that it still has these really obvious sort of dual spiral arms that are sort of winding out from the center. Now, the reason this object's a little tricky to 3D print is because, again, the color gradient's not very high, so those arms are quite faint. Everything else is a very gradual change in color. So this one can be a little bit tricky to 3D print just because of that really gradual change. So when we make our models, we do have to be a little bit careful about the color contrast. yeah, these red spirals, they are really, really interesting objects. They're worth including for us to talk about with the people that we work with, because they're an unusual kind of galaxy. We think that they mostly come about by interacting with other galaxies. So in the same kind of way that M51 is interacting with its companion and M101 also interacted with its companion, what we think has happened in most of the cases where red spirals exist is that they've really gently had most of their gas stripped away by galaxies that have come close, but not close enough to sort of destroy their shape. So if we remember the mice that Katya showed us before, those two galaxies that maybe looked a little bit like spirals still, but not so much anymore.
Mhm.
Yeah, you can sort of tell those used to be spirals. They're not really though. So this isn't the mice. This is another example of two interacting galaxies. But you can tell they used to be spirals. They're not really spirals anymore. Those have had a really, really close encounter. Whereas we think in the case of most red spirals, at least red spirals that exist in galaxy clusters, they've had their gas stripped away. And so they've lost their ability to make stars. Over time, their spiral arms will fade away and they'll just look like disks with a little bulge in the middle. So they'll look a little bit like lenticulars possibly. But we've caught them at just the right time. Basically, we exist at the right time in the universe to be seeing these kinds of galaxies nearby to us because they've had long enough to have that process happen, to have their gas stripped away slowly enough so that they still keep that beautiful structure, but they lose that ability to make new hot blue stars.
How long is that window for those spiral arms to slowly fade away?
So again, I mean, nothing when it comes to galaxies happens particularly quickly.
Right.
So even short-lived stars, so the really massive blue stars that give blue galaxies most of their color, will last for sort of hundreds of thousands of years. And we think, I mean, that's pretty fast for a star to live out its life. So the arms will probably spend, I'm kind of guessing here, my guess would be it'll be probably another billion years or so before those actually fade away.
Gotcha. All right. Do we want to go back to those models, the 3D
Yeah.
prints?
Why don't we jump back? So basically, so this project started in 2016, we did some test runs with models. We realized very quickly that my idea was okay, but what we really needed was the opinion of as many other blind and vision impaired people as we could possibly get. Because like I said before, everybody with a vision impairment is unique. Everybody learns differently. Everybody needs something slightly different to make things work for them. So we made some prototype models. We made models that were different sizes. We made models where the tactile features were really high and spiky, and other models where the tactile features were really, really subtle. Kind of, you had to really feel them quite carefully to actually pick anything up. And we took those out to. We found vision impaired students in nearby schools. We found support groups for slightly older vision impaired people, and we basically talked to them about astronomy and sort of got them to give us as much feedback as they possibly could. And so Katya's got a picture there of us basically chatting with some students from a nearby school. These kids were absolutely amazing. They were very forward with their opinions. They were not scared to say, "Hey, this isn't working. You need to make a change." And I think that's really important. But they were very complimentary when things were working well as well. So they gave up a lot of their time. They loved learning about astronomy because for a lot of them, it's something that they didn't think they would be able to learn about. They'd never really thought about as being something they could be interested in. So I think for me, at least, as somebody who loves astronomy, having that chance to talk to these young people and show them that astronomy was something that they could actually access was yeah, really, really, it was just a really nice thing to be able to do. But so based on their feedback, we actually introduced a lot of features into the models that we didn't originally have. So we did things like printed these really big full color images to go along with these models so that people with a little bit of vision could look at those while they were feeling the models. We did things like putting the images on the back of the models. And if we just zoom in to those, that array of 6 models off to the right for a second, Katya. Yep. So you might be able to tell that running around the edge of these models is a raised bit. So this is another bit of feedback that we got from the people that we talked to, This is something we wouldn't have come up with on our own. This raised edge is the same height as the highest tactile feature in that model. So if you can imagine bridging your hand from that edge across to any part of the model, you'll be able to tell how close to the maximum brightness or the maximum height of that tactile feature you are when you're feeling any part of that model. So it's just a way for people to work out where they are, what they're feeling, how bright that feature actually is. So yeah, we got so much useful feedback. The models are so much more accessible and versatile. They work for a wider range of people. What we're finding now is that they actually work really, really well in mainstream classrooms that have a mixture of vision impaired and fully sighted students. And so the advantage is we can give everybody in the classroom the same resources to use at the same time. Everybody works together. Everybody has the same restrictions and the same accessibility, I guess. So nobody has an advantage. Nobody is being pulled aside and being told, we're going to give you this special thing so that you can learn this. So everybody in the classroom is using the same stuff. And what we're finding, at least for some of the students, is that that's actually building a bit of dialogue between the students with vision impairments and the students who are fully sighted. And they're starting to talk to each other about their experiences and what it's like having perfect vision or what it's like having a vision impairment. So we're sort of helping those students to build those social skills as well. So once we'd finished doing all those tests, once we worked out that, yeah, we wanted to work with school kids, we wanted to show kids that astronomy is something that they can do even if they have a vision impairment, that there are always ways of working around whatever vision they might lack. That there's always some way that we can find to basically do what we want to do. We kind of realized that having a small team, so our team at Portsmouth at the university here is about 4 people. So it's myself, it's the outreach and public engagement manager, it's Coleman, who I've spoken about before, who basically designed these models. And we have 1 new member at the moment. So the UK is a pretty big place. It's not as big as the US, but it'd be a little difficult for us to get these resources out to everybody that we really wanted to in the UK. So in 2018, we got a little bit of money from a funding body, kind of the equivalent of the National Science, the NSF, is that National Science Foundation?
National Science Foundation.
There we go. I'm not American, so I don't have to know that. But so the UK equivalent, which is called the STFC, they gave us some money, and the idea was they wanted us to actually go out and start training people. So other science communicators, other academics, other researchers, people who would possibly want to take these resources and bring them to the vision impaired community nearer to them and start showing them that astronomy is accessible as well. So we spent 5 months traveling around the UK. We ran 5 workshops for 66 people. While we were doing all of that, we also built a whole lot of resource kits. So we made lots and lots of copies of our sets of galaxies. We made enough different models of galaxies to basically tell a story, to start off with a spiral galaxy, go all the way from a spiral through galaxy that's merging, all the way to an elliptical galaxy, which is the sort of the final product of a galaxy that's merged with something else really, really big. So enough galaxy images to basically talk about galaxy evolution, to talk about what the colors of galaxies, what the shapes of galaxies can tell us. And this is a shot from one of those training sessions. So this is the one we held in London at the Royal Astronomical Society. You can see in the background there are just shelves and shelves and shelves of old books. So this is a pretty grand old building. I don't even want to think about how much this wooden table in the middle there would probably cost if they were to try and sell it. But yeah, they let us set everything up on that. You can see everyone sitting around that table is really engaged. So this is the first time we've given them the tactile models to feel. We haven't really explained what they are though. So the idea is we wanted people to feel those models and talk to each other. So start thinking about the language that they were using to describe what they were feeling to us, whether that language was accessible, whether that language would be understood, useful to somebody who couldn't see. We were actually lucky in this workshop. So the woman in the bottom left-hand corner of this image is actually completely blind. So she is an actor. She runs a theatre company. She wanted to try and work out whether models like this could be useful for some of the stuff that she does. because she does shows for people with vision impairments. She tries to do slightly more inclusive stuff. There's also a young gentleman in the top right-hand corner who is also totally blind. He's doing a physics degree at the University of York. And so you can see that he's sort of feeling the models and describing them to the people sitting around him as well. And I think there's another completely blind gentleman sitting down the other end of the table as well. But this is just one of the things that we did during the training sessions. Because a lot of the people who attended these had never tried to communicate science to people with vision impairments, we also tried to, I guess, dispel a lot of the misconceptions that people often have about somebody with a vision impairment. So the feedback we got from people often was, but I'm afraid of saying stuff because I might offend somebody. And so making people realize that it's actually really hard to offend somebody with a vision impairment, I think was really important. So obviously being careful with the language that you use to some extent is important. We can still say things like, oh, I see what you're talking about, because that doesn't literally mean that you see what someone's talking about. It's just a turn of phrase. It's an adapted bit of language that everybody uses. It's not a literal thing. So we spent as much time as we possibly could making people feel more comfortable, making them feel like they weren't going to offend people if they tried and if they talked. Yeah, so those training workshops are really, really important. And while we were doing those training workshops, we were also making these physical resource kits. And I think we have a picture of, there we go. So that's a stack or 3 stacks of 15. So we made 20 of these in total. This has a full set of those multicolor tactile galaxy images. It's got a whole lot of other weird and wonderful stuff. So there's about 35 tubs of Play-Doh, a whole lot of blank CDs, some tactile stickers, some rolls of paper, basically everything that anybody would need to run any of the workshops that we put together to run with school students. And so for people who'd attended our workshops, we got them to submit an application and say why they thought they would be able to use one of these resource kits. And we chose 20 of those people. We sent the resource kits out to them. And now they're working towards using these resources in their own part of the country, talking to people with vision impairments about how awesome astronomy is using these resources. And yeah, the Play-Doh and the CD, if you're wondering, that's to actually make a toy model of a spiral galaxy, just to get people familiar with the shape of a spiral before they dive in and start using the proper tactile images of the actual galaxies, because obviously they're a little bit more complicated. If we can build ourselves a model of a spiral galaxy using some Play-Doh and a CD, it's a much easier sort of step up to that real data. So that's what we've been doing since 2016. It doesn't seem like that long. We've expanded from just operating in the Portsmouth area, so down the very bottom of the UK, to covering most of the UK now with all the resource kits that we've sent out. It's really, really exciting to be working on a project like this, and being able to help to inspire young vision impaired people, show them that, yeah, if they want to do something really visual like this, they totally can.
Yeah, and this is such a cool project. Now, I got the pleasure of meeting you in person last summer.
Yep.
Can you tell us a little bit about your involvement at Yerkes? Or I guess it was 2 summers ago already. So
Yeah, so I've been coming to Yerkes since, when was it? I want to say 2016. It might have even been earlier than that. So basically, Kate has invited me back to Yerkes once a year to come and help with so some of the outreach that used to happen at Yerkes Observatory before it was closed. Hopefully that'll open again and it'll thing. But all that wonderful stuff that is transferred over to Glass Education. So I did a little bit of work with Kate and everyone else on stuff like that. But I've also helped out with the iData project, which of course Glass is still heavily involved with. And so this was an initiative to try and make a telescope, so a virtual telescope interface, accessible to people with low vision or no vision, and a whole lot of workshops that are tied to that to explain things like how CCD cameras work, how light is collected by CCDs, how telescope filters work. So all of that stuff tying into how we get images of galaxies that just pick up the red light or just pick up the blue light or other things like that. So all of these really visual concepts, the people from iData worked out ways to talk about all that different kind of stuff, and also to get young people into coding using a programming language called Quorum. And so I've been coming over once a year to basically see what's happening, to talk about what I think's working, what I think isn't working, to just look at all the amazing stuff that Kate and everyone else working on glass, of course, or yeah, Katya and yourself as well, and just sort of help with that. And I'm actually really sad I can't come and visit this summer, obviously, because of coronavirus. But I think I got to say thank you so much for letting me talk tonight, because it actually feels a little bit like I'm back in Williams Bay, just for this hour.
So yeah. Nice being able to catch up.
It has been, I mean, really the last 5 years visiting Yerkes has just been the most amazing experience for me, just being able to work with such a wonderful people, and also being able to visit the site of so much wonderful astronomy over the years as well. We all know just how many amazing people have gone through Yerkes over the years. The amazing science that's come out of that, and just the amazing inspiration for so many young people as well visiting that site.
Yeah, I couldn't agree more, and I really hope projects like this get to continue to be involved with at Yerkes, because myself personally, I had never really thought about how visual a science astronomy really was. So something that had never occurred to me, but finding and seeing these actual models helped me better understand these galaxies. And I think that's one of the coolest things about them, is that they're a great educational tool for everybody.
I think that's definitely what we found. So especially if we take these out to science festivals, we find we're able to engage people for a lot longer. So normally, if you've just got stuff for people to look at, they'll come past, they'll take a glance, and then they'll walk away. Because we're physically handing things to people, because their hands are occupied, they're trying to feel stuff while we're talking to them, we actually keep them there for a lot longer. We talk to them for a lot longer. We can provide more inspiration, more sort of, I guess, increase their knowledge of the stuff that we're talking about as well. So yeah, they have a lot of advantages. And yeah,
and it levels the playing field for everyone.
It levels the playing field for everybody. I think what we're really trying to show as well is that universal access is something that helps everybody. So the more modes of interacting with something, or the more ways of interacting with something that you can introduce, the easier it's going to be for everybody, that thing. So we are developing these for vision impaired people, but this is the kind of resource that's going to help everybody in the long run. And going forwards, that's very much what we're trying to do as well. We introduce sound. We want to keep the tactile, keep the visual as well, but just give people that extra way of sort of stuff. You're trying to play one of the movies, I guess.
Yes, there was one, the M51, that intrigued me. That I hope my computer decides to.
Well, as we hope for this video to play, allow me to just thank you again for taking the time to come and hang out with us. Hopefully we'll be able to get you out here next summer or the summer after, and continue to work on cool projects like this.
I'm really, really looking forward to being able to come back and visit again. But like I said, thank you so much for letting me talk this evening. It's been really, really wonderful. Oh, that almost worked. Almost worked.
Oh, we have a question for you.
Yep.
Bob Kaplan would like to know, were you at Starlight 2018?
You might need to remind me what that is.
I don't remember you being there.
I don't think I was there. So 2018, I believe I was in Williams Bay. When was it? It would have been July or August, I think.
Yeah, Starlight was in May. It was like Memorial Day-ish weekend.
No. So I missed Starlight, unfortunately.
Yes. All right. So yeah, because somebody was showing stuff like this there, so clearly some of the cool models that you left at Yerkes were getting used during that time.
Quite possibly. So one thing I should point out as well, and I completely forgot to say this. So even though we made those physical resource kits, we made those available to a select sort of number of people. Yep. So the movie Katya's got there is that's one of the models that we make with the image kind of laid over the top of it. So you can kind of see what I mean about the brighter parts being higher, the dimmer parts being lower. So you can almost think of it like Braille, but it's like multi-level Braille. So yeah, as well as making these resources physically, so 3D printing them, we've also put everything online so that anybody can access everything digitally. So basically, if you have access to a 3D printer or you're willing to put a little bit of money down, send the files off to somebody to print them for you, you can do that as well. If you go to our website, you can get the lesson plans, you can get the models. We really wanted to make sure that we didn't want to charge anyone for any of this stuff. We wanted to make sure that it was freely accessible to anybody who wanted to use it. So yeah, if anyone wants to print a galaxy and feel it, then go for it.
And if anyone wants any of these images afterward, they also have a list of image descriptions for them,
which are
so
way
if
too
anyone
detailed.
in the if anyone in the audience is visually impaired and wants a description of all the images that we've shown tonight, we can put this out, or just let us know and we'll email this to you.
And I was planning on putting either a link to all these images with the image descriptions, or putting them up on Facebook, so we can share out this video, and you guys can share this conversation with others, and hopefully we keep having cool conversations like this. So thank you once again for joining us, Nick, and I think we are all set. So
Thanks so much for having me. Have a good afternoon, everyone.
Thank you. Have a good evening.
Thanks.